Hello everyone, welcome back to part 2 of our lecture on erosion. So where we left off, we had just talked about weathering and mass wasting processes. And now we're going to talk about erosion specifically. So erosion is the transport of rock and sediment from one location to the other. So after it's been mass wasted and gets off of the hill slope, then it gets eroded and moved somewhere where it eventually gets deposited. And there's a number of different erosional processes that can drive this this action. The first of which is hydraulic action. So this is when the force of water or air moves rocks itself. So hydraulics is the study of fluids. So both water and air are fluids, and so they can act on the rocks themselves and provide pressure to crack a rock and move it somewhere else. There are a few different types of hydraulic action, and so that can include just flowing water. As water flows over a rock, such as in a river, that rock can be moved somewhere else and eroded away. Additionally, along the coast, you still have erosion as well, and you can have waves crashing or waves as well on a river. And so you can have continual wave action along the shoreline, and that can move material to a different location. Hydraulic action also involves air compression. So whenever you have a crack in a rock, that crack is filled with air, but when as a wave or as a river flows quickly into that crack, that air is trapped, and it can experience really high pressures, and that pressure can cause the air to shoot out or apply pressure to the rock. And as a result, it can spew out material and further fracture the rock. And so that's how air tends to provide hydraulic action and is an erosional process. The next erosional process is abrasion. So this is when rocks are thrown against a cliff face or a riverbed. So it's rocks that are transported by the fluid itself, and the banging of rocks itself is what's causing the movement of new material. So then after that, we have attrition. So this is when you have several rocks within a water body, and along the bed of a river or on a beach, these rocks are banging into each other, and that banging causes them to wear down into smaller and more round particles. And so while abrasion is erosion against the bedrock or the bed of a river itself, attrition is material that's already been weathered away and is now banging against each other. And so that can cause further movement as smaller, more rounded particles tend to move more easily. And then lastly, we have solution and corrosion. So as we talked about with chemical weathering, that chemical reactions can occur in order to weather a rock. After that occurs, then you have the ions dissolving into the solution, in this case water, and being transported away as the water flows to a different location. This most significantly happens with carbonates, but it can happen with salts and other minerals that we've talked about. So that's another way that rock can be moved to a different location. And so the predominant erosion occurs at rivers. So rivers are very good at transporting material from one location to the next as they flow. And so a river can either build up sediment or it can erode it away. And so we call those two different processes degradation and aggradation. So degradation is when sediment is deposited within degradation is when river is removed from a river, and that river starts to incise, as you can see here, whereas aggradation is when sediment is deposited in a river and you start to have a buildup of material. And so as you have sediment getting eroded and moved through a river, whether it there's degradation or aggradation depends on the power of that river. So we can see here, when does a river erode? When is it in degradation versus when is it in aggradation? And everything is in the balance. So the two different factors that really have the most significant impact are the sediment grain size as well as the stream slope. So if we look at this diagram, we see that as you get larger particles, more coarse grained, then that river has a harder time transporting those coarser grains. And as a result, you have aggradation as the sediment can no longer be transported and starts to be deposited along a river. Whereas if you have the sediment size decreasing, you have finer sediment, then the river more easily carries that sediment and you have degradation and erosion of that material. The same relationship happens with stream slope. So as you have steeper streams, then that river can transport material more easily, so you have degradation. And if you have a flatter stream, then it can carry less material, it has less power, and therefore you have aggradation. So sediment moving within a river channel requires some amount of activation energy. So a sediment grain can get kind of stuck within the riverbed, but once it's actually moving, it can transport a little bit more easily. And this is indicated by the Hjulström curve, which dictates the velocity needed to move a sediment grain based off of the diameter or the size of that grain. For example, if you had a 1 millimeter sized grain, it would be deposited in a river if the velocity was less than 1 meter per, or 10 centimeters per second. Whereas in order to get that grain to actually move and get eroded, then you would require at least flows up to 2 or 3 centimeters per second. But then once it's off of the bed, you only need the velocity to stay over 10 centimeters per second for it to be transported. And so this diagram kind of shows that concept of the activation energy, and that activation energy tends to be closer to the transport energy as you get to larger grain sizes, because at smaller grain sizes you have interactions between different clay particles. They tend to have electrical forces and more atomic forces acting on them that kind of stick them together. You may have felt mud before and it's kind of sticky, and that's why it takes not more energy, but more energy for the grain size itself. So as you have erosion occurring in a river, you start to form meanders like the one you see here. And so there's erosion occurring on this cut bank here. And so the result of that erosion is that on the outside of a curve in a river, you have water that's moving relatively quickly. You can see this cross section C here. The outside of the curve is the deepest and has the fastest water, whereas the inside of the curve is fairly shallow and has the slowest water. And this is because as you have erosion occurring on the outside of the curve, you have sediment that's getting eroded here. And because you have the slower flow here, that sediment gets deposited in that slower current, and you have the stream moving in the direction of the outside of the curve. And so it'll start to erode here, and it will deposit here, and the whole river will shift over to the right. And we can see that here in this animation that this river is changing its course just because of that erosional process. And you can see the meander beds getting further and further as they push out towards the outside of their curves until they eventually get cut off by their own flow and find a different path. So also, waterfalls are an important erosional feature within rivers, and maybe you'll have a chance to see a beautiful waterfall like this. And so waterfalls form whenever you have a very hard rock over a fairly soft rock, a rock that's hard to erode over a rock that's more easy to erode. And as a result of that combination, you have that hard rock that requires the sediment to be eroded away underneath it before it actually falls. And so you'll start to have the erosion of that sediment, that layer, coming all the way up and eroding it away until that hard rock is overhung and it just topples over. And as that water falls down the waterfall, it picks up a lot of speed and will erode the material more underneath the waterfall and cause a plunge pool where you generally have a pool of water underneath the waterfall. We can see here, this is the distribution of river discharge throughout the planet. Bluer areas have more river discharge, and this can give us an idea of how much sediment is being moved in these different areas due to fluvial erosion. And so here's a map that shows all of the different river outlets into the ocean throughout the world. And so the sediment load in megatons per year is mapped, and you can see here that the largest rivers are in Southeast Asia and the Amazon, and can produce a lot of sediment. But sediment is produced pretty much all over the coastline of the world. And so fluvial erosion is a big factor for moving sediment. We can put some numbers to this and see that that Southeast Asia is definitely the largest component of sediment transport from rivers. It produces 12 billion tons of sediment per year. And that's just because you have a whole lot of rainfall in this region, as well as a lot of mountains that are recently being made in the Himalayas. And so you have a lot of erosion occurring. And so you can see here these different continental regions and how much they end up producing in terms of fluvial erosion. With climate change as well, the distribution of river flows is expected to change. Certain areas like northern Canada and Southeast Asia are expected to have more river flow, whereas other regions such as southern Europe and southwest United States are expected to receive significantly less. And so that is going to also impact how sediment distribution is changing throughout the planet, and where the nutrients that come from that sediment are going to be distributed throughout the ocean. Another major factor too with fluvial erosion is that people like to build dams. We have dams all over the planet, and you can see here that a wide variety of rivers are in sediment deficits for how much sediment that they release into the ocean, just because they have a lot of dams that are backing up that sediment and storing it. And so if we're going to figure out how much sediment is released through these systems and how they might affect nutrient loads and all these different concepts, that we need to also factor in how the dams might impact that process. So next we're going to talk about wave erosion. It's a major erosional factor for changing coastlines. And so a lot of times when you have a fairly sturdy sediment layer that forms your shoreline, you can have the formation of a bay and headland system. So this is when you have this steep headland wall that develops, as well as bay inlets in the other regions. And so this forms as you have a series of hard rock and soft rock in sequence along a shoreline. And so as you have waves hitting this shoreline, then the soft rock erodes and forms a bay, and it leaves behind the hard rock in the form of a headland. This process goes to a point and exaggerated by the fact that as a bay develops, it gets a stronger ability to refract waves away from it, and those waves tend to instead hit the headlands, and that wave energy goes into that stronger material instead of the bay, and it can kind of reach an equilibrium point as the headlands dissipate that energy away from the bay. And so, yeah, that's you can see the convergence of wave energy into those headlands. As waves erode away at a headland, they tend to form a series of sequential geomorphic features, from caves to arches, such as the one that you can see here, a very pretty archway, to stacks and stumps. And so the first of which are caves. And so as you have cracks develop within a headland, as you have wave erosion occurring, those cracks can develop into a cave, and eventually that cave might go all the way through that headland wall and form an archway, where you have significant undercutting, and this archway forms in the headland. If that headland then collapses and the archway collapses, then you have what remains is a stack, which is just a column of rock formed from a previous headland. And then eventually, as time moves forward and you have more erosion occurring, then you have just a stump that's left behind, and that's just a rock pile that's been eroded from a stack. Additionally, you can have the formation of blowholes. So blowholes develop whenever you have an erosional feature within a headland in which you have an opening where water can enter through wave action, and then it is forced out of a small hole in the rock. And so you can see that diagram here where the waves force water into this channel, and it gets forced out through this hole in the top of the headlands. And this funneling can kind of further this erosion and form this kind of feature. And apparently it's very fun to throw tires into blowholes, and this kind of shows just how powerful the water that's blown out of these blowholes can be, just because of all that pressure that is stored within them. So beaches are defined by their wave balance, or their sand balance. So a beach will erode and experience more erosion if it is out of balance. So what does it mean to be in balance? So that means that the sediment that's being input into the system from coastal erosion as well as from rivers depositing sediment, that has to be equal to the amount of sediment that is washed away. And there's a number of processes that wash away sediment, but if it's out of whack, then you start to erode your beach away. And so you can see here that the sediment that's deposited can go into sandbars or deeper into the ocean, and that sand then moves towards the beach through waves from storms and small waves, but also gets washed back by gravity, as well as moved away from the beach by wind, and so as well as a longshore transport that can transport sand along the coastline. And so if this beach was to sustain itself, it has to make sure that the input of sand from rivers and the coast is equal to the amount of sand that's leaving through a longshore transport, wind erosion and overwash, and gravitational removal of sand. Sand is very important, and we tend to like our beaches, and so there's a number of man-made features that have been developed in order to try to reduce wave erosion. One of those being groins. These are man-made structures that act as kind of peninsulas out from the coastline, and what they end up doing usually is that they deposit material on the upshore region, and then down the longshore drift, where down current, you have erosion, so removal of sediment, and so the waves tend to circulate back and form an eddy, and they can erode material on the down slope side of the shoreline. And this is a good thing if you're trying to maintain sediment deposition in this updrift area, but not so much if you're trying to preserve sediment in the downdrift area. Another feature that has been developed are seawalls and breakwater walls. And so these just reduce the amount of energy of the waves that come and impact the beach. If you have a very strong storm that can wash away a lot of sediment, and so by just reducing that energy, especially if there's a river coming in and depositing more sediment and not getting washed away, then you can have deposition occurring inland of the seawall. Another feature along the coast that you might have seen is a spit. A spit develops whenever you have significant longshore transport of material and the beach shoreline rapidly changes direction. So you have this sand getting moved down the shoreline, and then the coastline changes direction and goes off to the left, and this current just continues, and then it loses energy and it deposits this sand and forms this small sand peninsula. And so that here is called a spit. Another cool erosional feature that we can see in landscapes are atolls. So whenever you have an island develop, especially in the tropics, you can have barrier reefs that develop along the shoreline. And so those reefs are corals or that can develop and grow. But sometimes those reefs can grow faster than the volcano can sustain itself, and so that volcano can erode away and slowly erode into the ocean, while still the reef can build up itself. So as the coral grows faster and faster to make sure that it's near the surface where it can get sunlight, then it will continue and sustain itself and form a ring, while the island in the center has completely eroded away. And what's left is that you have that ring of reef on the outside with the entire island that's been eroded away. And you can see that an example of that here, very nice, beautiful oasis that develops. And then the last concept that we're going to be talking about in terms of wave erosion is the Bruin rule. So Bruin was a guy who liked to study coastlines, and he wanted to figure out what was the impact of sea level rise on coastal retreat. So we know that as the sea level rises, it's kind of acting as if all of the waves are slightly larger, and so therefore they can erode more material away. And so we want to be able to quantify what that amount actually is. What is the proportion of the sea level rise to how far the coast retreats as a response? As his calculations showed, what results is that for every meter of sea level rise, you tend to have 100 meters of coastal retreat and erosion. And so there's a 1 to 100 ratio between sea level rise and landward coastal retreat. And so that's really significant. So New Jersey, for example, is expected to receive 3 feet of sea level rise by the end of the century, at least, potentially significantly more. And as a result, we expect as well that our coastlines will, unless fortified, will also retreat by 300 feet. And so that's very significant if you have coastal communities that are living within 300 feet of the shoreline, then they're going to be significantly impacted by more storms, and they might just completely get washed away if they don't have any plan for coastal replenishment. So you can see here a map of the probability of coastal erosion over 3 feet per year, which is a fairly quick erosion rate. And the areas around New Jersey tend to be some of the highest rates of erosion, largely just because we have fairly low slope beaches and a lot of sea level rise. And so we're somewhat likely going to experience significant rates of shoreline erosion that result. Next, we're going to be talking about Aeolian erosion. So this is erosion that occurs due to wind. So wind is a very significant factor for erosion and for transporting sediment from one location to the other, especially in dry climates such as deserts. And one interesting feature that occurs in deserts is desert pavement. So in a desert, you have usually a combination of fine sediment and coarse sediment that's mixed together and forms the soil. And so the wind has an ability to blow away that fine sediment more easily. And so as a result, those larger pebbles are left behind, and they start to concentrate on the surface. And once they completely cover the top surface, they are kind of armoring the soil and prevent further erosion. And so the result is that you have what's known as a desert pavement, where the surface of the soil in the desert has significantly higher grain sizes than the sediment below it. And you can see that here, where all these larger rocks have been are covering the surface and forming that desert pavement. Also, that desert pavement tends to have a darker color as it's exposed to the sun more readily. Additionally, wind can cause sandblasting. The wind can pick up a significant amount of sand as it blows, and that sand can blow against a rock and act as an abrasive and erode away that rock and cause a polished surface. Additionally, if that rock rotates or the wind direction changes, then you can have multiple polished surfaces on a rock. And you can see that here. This rock has been sandblasted, and it's left this curved surface, as well as this one here from when it has rotated previously. Another cool feature is ventifacts. So ventifacts are rock formations that are formed from aeolian erosion. So that previous rock was an example of one, and this is another example this is a picture that I took in Antarctica. I was working in a location called the McMurdo Dry Valleys, which is one of the few locations in Antarctica that's not covered in ice. It's a ice desert, so there's not enough snowfall to actually form glaciers there. And so there's also a lot of wind in that location. And so the wind blows a significant amount of sand and hits these rocks. And when the sand gets trapped in these holes, and it kind of bangs around, and it forms these holes as a result. And so this whole rock would be known as a ventifact because it's shaped by wind erosion. You can also have the same thing happen on ice. So we were working on an ice-covered lake in Antarctica. This is Lake Joyce. And you can see these crazy different ice formations that develop both as a combination of differential melting as well as the wind just blasting these different features and forming these intricate patterns as the wind blows in complex ways. Additionally, aeolian erosion creates dunes. So dunes are these mounds of sand that can develop in a desert region, and we're going to talk about dunes much more significantly in our desert lecture. So I'll save talking about that any further. Additionally, we have loess, which is whenever you have a significant amount of silt that's deposited by wind, you form loess. So loess are extensive deposits of silt by wind. And they tend to have this kind of yellowish hue as they slowly erode and get exposed. And this is actually a significant process because there's a lot of silt in the world. So silt can be developed by glaciers or by frost wedging up in the mountains or by volcanoes ejecting it out. And then that material gets transported into rivers and gets washed out into a floodplain, or it moves into a desert landscape and goes into a dune formation. And as that area gets exposed to wind, that silt will blow and deposit into a loess formation. And so areas where you have a lot of these processes occurring can have extremely extensive deposition as loess. And you can see a map here that shows that loess actually covers 10% of the total area of the planet. So it's not anything to scoff at. And some of the largest areas that are covered in loess are in the Midwest of the United States. And the reason for that is because of the fact that there was a large glaciation that covered all of northern North America in ice during the last ice age. So we had the Laurentide ice sheet as well as the Cordilleran ice sheet that produced a whole lot of silt as a result. Remember, we talked about rock flour and how glaciers weather rock. And so that material gets pushed out by the glacier, and then you have strong katabatic winds that we previously talked about as well that flow down glacier, and then they deposit that silt downwind, and now you have a whole bunch of loess that's developed where the ice edge used to be. Another maybe surprisingly important factor for erosion is splash erosion. So as a raindrop falls, it can strike a surface at roughly 5 to 20 miles per hour, and that striking of a raindrop can provide enough energy to erode a surface away and provide that activation energy for that sediment to be transported somewhere else. And depending on the properties of the rain and of the sediment, that sediment can be pushed significant distances, such as 5 feet away. And you can see an example here of a landscape that's experienced significant splash erosion. These little tiny pillars here are where you had pebbles, and where the pebbles shielded the ground from the rain, and so it didn't get eroded. So if this was just a rain landscape that had a flow of water over it, then these little pillars would be eroded away as well. But the fact that it was splash erosion occurring made these little pillars survive. And so the amount of erosion that results from splash erosion depends on a few different factors, one of them being the grain size. So the smaller the grain size, the more easily that splash can transport that material. And also the slope that grain is located on also has a major factor. So it's easier to transport a grain that's on a steep slope because it just requires a little bit of energy in order to have it start rolling down that slope. Additionally, the velocity of the raindrop is obviously important. The faster it falls, the more easily it can erode material, and also the rainfall rate. If the surface is constantly pummeled by rain, then it can more so erode the surface. So that's splash erosion. And we can see examples of splash erosion even in the rock record. So these are fossilized splash erosion marks, and we can use these to tell interesting things about the weather processes that happened when this rock was initially formed. And then the last erosional process that we're going to be talking about is glacial erosion. So this is a picture of the Gilkey Trench with the Gilkey Glacier moving through it that I took last summer when I was working out of there. It's a beautiful glacier right near Juneau, Alaska. And so glaciers are really important for producing sediment in cold regions. One of the main reasons is because of glacial plucking. So as a glacier moves over a rock, it both abrades against the rock, so it rubs sediment against it and can scrape away at it. But also as it moves over a hill, then it can do what's known as glacial plucking. So it will pull away at that rock and strip that material away. And so that low pressure that develops relative to the opposite side of the hill can pluck material off of it. And what forms is known as a roche montagnais. And you can see an example of that here. This is Lambert Dome in Tuolumne Meadows in Yosemite. Beautiful mountain. I highly enjoy or highly recommend visiting it one day. So this is an example of a roche montagnais as the glacier that formed it flowed over this more shallow sloped side and abraded it, and then as it flowed over top, it plucked material off of it on the leeward side. So glaciers produce a whole lot of rocky material and sediment, and so that the sediment that results from glacial erosion is known as till. So the till tends to be very poorly sorted. Glacier doesn't really care that much how big of a rock it is. It's going to be able to transport it no matter what. Additionally, glaciers grind up rocks very easily, and the result of that grinding process is rock flour. So that it's a sediment that's very fine grained, so it's silts and clays that's produced by the grinding of rock underneath a glacier. And rock flour can go into a river or a fjord and change the color, and sometimes it produces some really beautiful color when you have white rock flour entering a blue lake. It tends to make these beautiful teal colors. So if you see a teal milky colored lake like this, it's most likely formed by glacial rock flour flowing into it. Glaciers also form U-shaped valleys. So as they flow downhill, they carve out the valley slopes and they form these wide valleys as a result, compared to more V-shaped valleys that a river alone would form. And so you can see this animation here. As the glacier forms, it widens the valley and erodes it away, leaving this U-shaped valley, and then is filled by a river that's significantly smaller than the valley that it flows down. Additionally, glaciers can pick up a lot of rocks and sand along their bottoms, and as it scrapes those rocks and sand along the bedrock, it can produce some interesting features. One of those features is glacial polish. So when there's sediment or sand specifically that's stuck to the bottom of the glacier, then as it flows along the bedrock, it can polish that rock just like a mirror, and it can be extremely smooth, just as you can see here. And that polish can stay there for several millennia sometimes. So it's a pretty cool feature in which the rock is polished like that. As you move to larger grain sizes and you start to move pebbles along the bottom of a glacier, you start to form striations. So these are marks made by pebbles scraping against the bottom of the glacier and into the bedrock below. This is a picture from Central Park as well, and that gives you a sense of just how far south that Laurentide ice sheet that I talked about from the last ice age actually came. It actually covered all of Manhattan. And then the last feature that can form is when you have a boulder that's moving along the bottom of a glacier, and it's bouncing along the bedrock and eroding as it does. And what results is known as chatter marks. So these are these concentric curved marks that form along the bedrock that all form in a row. And the interesting thing about chatter marks is that they can tell you which direction a glacier was moving millions of years ago. For example, you can think of that boulder bouncing on the rock like a cone that's being pushed into the rock. And depending on the slope of that bedrock relative to the direction of the glacier, it'll leave concentric curves in different orientations. So if the bedrock slope is in the same direction as the glacier movement, then the back of that cone will hit the surface first, and therefore the curves will point down the glacier motion. Whereas if the slope of the bedrock is opposite to the direction of the glacier movement, then the front of that cone will hit the surface first, and that those concentric rings will point opposite to the glacier motion. So that's how we can figure out how glaciers moved millions of years ago and do paleoglaciology. So that just about covers what we're going to be talking about in terms of erosion. So in summary, we talked about chemical weathering, physical weathering, mass wasting processes such as debris flows, and we also talked about erosion, including fluvial erosion, wave erosion, aeolian erosion, splash erosion, and then just glacier erosion. So thank you all for watching, and I will see you all in the next video lecture.